Hello everyone, welcome to my channel Chemistry is Fun. Today we will study a new aspect of the gaseous state, that is van der Waals equation. Now children, we have studied the gas equation, general gas equation, which states that PV equal to nRT. Now this equation will be followed by those gases which are either we can say perfect or ideal. But actually, under ordinary conditions, there are very few gases which nearly behave as ideal or perfect. And these are the gases which have very low boiling points, like nitrogen, hydrogen, etc. So, we can say that the gas which follows all the postulates given by kinetic theory, or which obeys the Boyle's law and the Charles law for every value of temperature and pressure, they only can be called as the ideal gas or the perfect gas, and they should follow the general gas equation, that is PV equal to nRT. But in reality, such gases do not exist. Actually, no gas is perfect. So we can expect a near ideal behavior for some gases like nitrogen, which have a very low boiling point. Because actually what happens at very low pressure, the gas molecules are widely separated. Since they are widely separated, there will be no effect of intermolecular attraction, because intermolecular attraction is actually present, which is not considered when we were writing the kinetic theory. So there was a faulty assumption we can say in the kinetic theory of gases, because we thought that it was postulated that intermolecular attractions are not present. And also the actual volume of the gas molecule was taken to be negligible. In reality, both these things don't happen. But still, at very low pressure, since the gas molecules are widely separated, the force of attraction between them will be very less, so they can exhibit near ideal behavior. But actually, if you say exactly, no gas can be termed as perfect. At a low pressure and a moderately high temperature, the real gases approach ideal behavior. The reason I just told, when the pressure is very less, the molecules are widely separated, so they don't exhibit intermolecular attractions much, and also the actual volume will tend to be negligible. It cannot be negligible, but since they are very far apart, so in the given volume the molecules are very far away, so their actual volume can be taken as quite less, so they can exhibit near approach to real gas. Means the real gases, they will give a near approach to ideal behavior. They are real gases only, but in the conditions I just maintained, they exhibit little bit of approaching ideal behavior. Now, just as I stated, there are deviations from gas laws. Under high pressure and low temperature, what will happen? When the pressure is high, naturally the molecules will be close to each other, so it is totally against the assumption that intermolecular attractions are not present. So why we find the deviations from the gas laws? The main reason is because of two faulty assumptions in the kinetic theory of gases. The first one being, actual volume of gas molecules is negligible as compared to the total volume of the gas. But in reality, we will see that the molecules are rigid spherical particles and they definitely possess a volume. So this assumption is also wrong, and intermolecular attraction is not present. This assumption is also wrong. Because of these two wrong assumptions or faulty assumptions, we can say that we find the deviations in the gas laws. Now van der Waals, he pointed out that in case of the real gases, the molecules do have a volume, and they definitely exert intermolecular attraction. So there is a mistake in the assumptions. To set the general gas equation right, to make it right so that most of the gases can follow it, he made two corrections. One was the volume correction, another was the pressure correction. Now in the volume correction, it is found that the molecules in case of a real gas, they are actually rigid and spherical and they occupy a particular definite volume. So, which was postulated that the actual volume of the gas molecules is negligible. That is not true. Since the gas molecules do occupy some volume, then the volume which is available for compression, that will become the actual volume minus the volume which is occupied by the molecules. Because earlier it was thought that there is no volume occupied by molecules, but this term now exists. We know that definitely the molecules occupy some volume. So B is taken as the effective volume per mole. Then what will be the ideal volume? Because V is the volume which also includes the volume occupied by the gas molecules. So that factor has to be subtracted. So the ideal volume will become V minus B. If there are n moles, then the corrected volume becomes V minus NB, where B is given as 4 by 3 pi r cube, because here r is the radius of the gas molecule. 4 by 3 pi r cube into 4n, where r is the radius of gas molecule and n is Avogadro's number. N is Avogadro's number. Because it was found that the excluded volume B is actually 4 times the actual volume of the gas molecules. So multiplied by 4n. 4 by 3 pi r cube into 4 into n Avogadro number we are doing. B is a constant. It is termed as the excluded volume and it is a characteristic of each gas. Next is the pressure correction. Next correction which we have to see is the pressure correction. Because see, when we take a gas in a container, the molecule which is present in the interior part of the gas, it will face attractive forces from the other molecules which are surrounding it. Because actually there is a intermolecular force. So in the interior of the gas, if we think there is a molecule, like say if this is the container having so many molecules, let's say this molecule at the center, it will face attraction from all the sides by other molecules from on all the sides. These forces are not so effective because they are equal and opposite forces and they will cancel each other. But when a gas molecule strikes the wall of a container, it will strike with less momentum because it will experience one inward pull, because now there is unbalanced attractive force, because the molecule is near the wall. On one side there is the wall, on the other side the molecules are pulling it towards them. So the momentum with which it should have struck the wall, that is not happening here. The momentum is less now because the other molecules are pulling it towards them. So there is an unbalanced attractive force. Since it is not able to strike with the required momentum, the observed pressure will be less than the ideal pressure. Ideal pressure means that condition in which the assumptions of the kinetic theory of gases should hold good. They should be correct, but it is not the case. So here the observed pressure will be less than the ideal pressure. So what will be ideal pressure? It is observed pressure plus P dash, where P dash is the pressure correction. We have to add a term because the ideal if we want to meet the ideal pressure, we have to add P dash to the observed pressure. That is the P dash is the pressure correction. The pressure correction also depends on two factors. First one is the attractive force which is exerted on a particular molecule which is about to strike the wall. So the molecule wants to strike the wall with some momentum, the other molecules are pulling it away. This attractive force which is exerted on the single molecule which is about to strike a wall will decide the pressure correction. And this is also proportional to number of molecules which are present per unit volume in the bulk of the gas, because more number of molecules, attractive force will be more. When attractive force will be more, its impact on the wall will become more and more less than the ideal pressure. So the pressure correction will become more. So the attractive force also depends upon the total number of molecules per unit volume in the bulk of the gas. The second factor is the number of molecules which are striking the wall. This also depends upon the number of molecules per unit volume. More the number of molecules, more molecules will strike the gas. So this is also proportional to the density of the gas. When density is high, number of molecules per unit volume will be high. So number of molecules which is striking the wall will also be more. So this pressure correction P dash is directly proportional to total attractive force. Higher the attractive force, higher will be the value of P dash. P dash is also directly proportional to D square. As I told you, it is dependent on the density of the gas. And it is inversely proportional to V square. We remove the proportionality sign. We have to multiply with a constant. So we get P dash equal to A by V square. So now the corrected pressure will be given by P ideal equal to P observed plus A by V square, because just now we got the pressure correction as A by V square, where A is a constant and it is the characteristic property of the gas taken. Now we can make both the corrections in the general gas equation PV equal to RT. Now when we do the corrections, we add the required values of the corrections. What we get? We get P plus A by V square into V minus B, because V has to be corrected and P has to be corrected. So P plus A by V square into V minus B equal to RT. Now this equation is known as the van der Waals equation. This is for 1 mole. If we have to calculate for n moles of the gas, then the same formula becomes P plus n square A by V square into V minus NB equal to nRT. So this is the final formula for n moles of gas. This van der Waals equation will be obeyed by the real gases over a wide range of temperature and pressure. So we have included the required corrections. I hope you all could understand the concept which I tried to explain today. Thanks for watching my video. Please subscribe to my channel. It will help me and you also. I will be posting new videos regarding chemistry again. Please subscribe to my channel. Thanks for watching. Thank you all.